Okay, so let's start off with the next, next part in the section 1. What we will be doing here is we will be looking into the analysis of your free fall, okay? Free fall with resistance and free fall without resistance. So first we will go ahead with doing free fall without resistance. And then we will be looking at bringing in resistance, okay? So there's no definitive form for bringing in resistance, but we would start to look at particular forms of bringing in resistance. Okay, so now, first thing what I'm going to do is, this is actually a revision question. So I will be starting a poll now. Okay, the question is, how many first order ODEs can the differential equation governing a freely falling body be split in two? Is it 4, 2, 9, or 1? So I'll start the poll now. You click in your responses. I wouldn't wait for a long time like I did last time. Okay, so be quick. Okay, so you can see the question now, hopefully. How many first order ODEs can the differential equation governing a freely falling body be split in two? "31 of you have voted. Okay, 48 participants totally. "20 more seconds left. "10 more seconds. Okay, so 8 of you haven't responded yet. I will be ending the polling now. Okay. So I will share the results with you. So 2 is the correct answer, and I'm pretty happy 30 of you have answered. Majority of you have answered. But the others, like, are you just clicking this in because you just want to like just not even read the question and just click something in and go forward? Because like we discussed this a lot of times, right? Okay, so how many first or ordinary differential equations can the differential equation governing a freely falling body be split into? The differential equation governing a freely falling body is a second order differential equation. So you can take a second order differential equation and split it up into 2 first order differential equations, right? Okay. The correct option is going to be 2. Majority of you did answer that, but 9, come on, like, why would you answer 9? One of you answered 9. People answered 4 and somebody answered 1. Okay, so 1, maybe you might have an issue with that. 2, yeah, majority of you did, but this is something that we've already done in the previous lecture, so you should probably be up to speed with that. Okay, so now let's just stop that and let's move on to discussing about freely falling body. Okay, so what are we doing here? Okay, what is the idea here? You basically take a physics problem and you want to do some numerical methods to try to find the solution. Okay, so the mathematical analysis of this freely falling body problem is quite well known, okay, with and without air resistance. So we want to try and do it in a numerical way. Okay, now one thing that I want to be very particular about this is you might be confused when you do see the results that this looks like projectile motion. Okay, so the results are to do with the values of the displacement as well as velocity. Okay, so the results will give you the plot that you see would look like this. Okay, and you would think that it's projectile motion, but it is not. We are going only in the x direction, or we are going only in the up down direction. Okay, we are not going in this direction. We do not have x and y. We're not going this way. We're just going in the up down direction. So the results can be quite confusing. Okay, and you might assume that it is projectile motion, but it is not. Okay, you're going in just one direction. Okay. So now let's look at this. Okay, so it's very easy to get confused when you see the plots of the results. You think that it is projectile, but it is not. Okay, I'm just reiterating that again. Now, the height y could be positive or negative based on the setup of the problem. So I'm going to giving you 6 different setups. Okay, and this should probably help you solve every problem that you come across. Okay, so if at all you get such a question like that, it's going to be difficult. If you do get a question like that in your paper, it's a difficult question. Okay, you do not get such questions, but I'm just covering all the aspects in the topic. Okay, so now in the freely falling body here without any air resistance. Okay, so the first setup of the problem will be, you will be standing at the top of a tower, which is about 10 meters long. Let's say it's 10 meters long, not 10 meters long for every problem. Okay, but say it's 10 meters long. And you drop the ball down. Okay, so you drop the object down. That is one way to look at it. So here, when you're doing that, and reaches the ground. Okay, so here when you're doing that, this particular ball is going to come down and reach the ground, right? At y equal to 0. The height becomes 0 then. So this is basically positive height. But when you do the solution for this using the Euler's method in a computer, okay, the computer will think that there is a hole here and it will go on to calculate stuff. Unless, of course, you put a condition where you say, okay, fine, if the height is going to be 0, stop the loop. Okay, if you put a condition like that, then you can stop it probably at, you wouldn't stop it exactly at the ground level, maybe a little bit higher or maybe a little bit lower. Okay, but you wouldn't go into this hole continuously. Okay, so that's the idea behind this. Okay, so let's look at the next one. The next one is where this next problem is where you stand on the ground and you take the ball and you drop it into a hole. Okay, that is your second way of looking at the freely falling body. The next way is to throw it up. Okay, and then it would come down. Okay, so don't get confused by the way I've drawn these arrows. It is still one-dimensional. Okay, it is only moving along the y-axis. There is no x coordinate here at all. Okay, so we're only looking at the y-axis. Now this, you still have positive height. Why? Because you're going from ground level 0, say, to about 50 meters and then coming down back to 0. So still you are going to be getting a positive height. Okay, now the next way, or the fourth way to look at it, is you are standing on top of a tower. So you do have an initial height already. You push it up to about 50 meters and then it comes down. Okay, below the height of the building. So it comes down to ground level. Okay, so it comes down to 0. That is your fourth way, and we have 2 more ways left. This is, you are at the ground level, you put an initial velocity, say v0, and you're throwing it up. It reaches a certain height and then it comes down to the ground. And then there is a tunnel in the ground, so it keeps falling down. Okay, now the one that I told you, which the computer basically executes. Okay, the computer basically looks at it this way. Say you have standing at an initial height of y0. Okay, you put an initial velocity v0. Okay, the initial velocity v0 is not 0. Okay, you put some amount of thrust. Okay, and then it goes up and then it comes down to the ground level, and from the ground level it goes further down into the tunnel. Okay, so I hope you don't get confused with this. There are 6 different ways you can set up this problem. Okay, everything is just free fall, but there are 6 different ways you can set up this particular problem. Okay, so in this case, what do you have? You do see in your results, when you execute it from the computer and you get your results from your program, you do see positive as well as negative heights. Okay, so the convention that we are going to be following here is, okay, typically the convention is going to be the coordinate axis convention. Okay, so here, if say you have this, if you're going in this direction, it's positive, right? If you're going in this direction, it's positive. If you're going in this direction, it's negative. And if you're going in this direction, it's negative. Okay, so I will cater all of these problems that you have in this kind of a format. Okay, so all you have to remember is the coordinate axis. So if there is a force that is acting this way, that force is going to be negative. If there is a force that is acting this way, that force is going to be positive. So that's how I've catered this. Okay, some textbooks, they alter the sign convention. So let's say here there is a force due to gravity that's acting as mg. I have put it as minus mg. There are textbooks that put it as plus mg, but then they alter the drag force or whatever that's acting this way. Okay, so we will discuss that a little bit further on. Now we've discussed 6 different ways that we can model this problem. So now what I'm going to do is I'm going to ask you a question. I want to know if you know this already. Okay, so be very careful because there is a little bit of trick. I mean, the problem is, the question is set up in a little bit of a tricky way. Okay, so do you think it is necessary to specify the mass of the object in the problem of the freely falling body with no air resistance? I will specify that again, no air resistance, if the terminal velocity is not given in the problem. Okay, let's read that again. Do you think it is necessary to specify the mass of the object in the problem of a freely falling body with no air resistance if the terminal velocity is not given in the problem? Yes or no? Okay, I will start the poll now. Please be a bit quick. Forty seconds left. Twenty seconds left. Okay, so I'm ending the poll now. Okay, 50-50 exactly. Okay, so some of you said yes, some of you said no. It's exactly halfway through. Okay, so you're confused. Okay, now I will just share the results so you can see I'm not lying. It's 50 and 50. So 50 of you said yes, 50 of you said no. Okay, so let's just analyze this in a bit of a way. Okay, so let's just split this up. Okay, so what am I saying? I'm saying, is it necessary to specify the mass? Do you require the mass of the object in the problem of a freely falling body? Okay, with no air resistance. I have specified that it's a freely falling body with no air resistance. The rest of the question shouldn't even matter to you. Okay, whenever I've said that, it does not matter. The weight of the object really, or the mass of the object really does not matter. Whether it is, say, a stone or whether it is, say, a feather, it is going to reach down at the same time if there is no air resistance. So if you're putting this in a vacuum, it is going to reach down at the same time. Okay, so what is it? Do you think it is necessary to specify the mass of the object in the problem of a freely falling body with no air resistance? No, it is not required. So the answer is no. Okay, so I hope you got that. If you haven't, let me know in the chat. Okay, so now the question of having terminal velocity here, is it even required? Terminal velocity happens when there is a drag force that is involved. If you have a drag force, then you do have a terminal velocity. Otherwise, you don't. Okay, so let's move on to the next slide. Okay, so in this problem, what would we be finding? Okay, you will be using the Euler's method to do this. Okay, the RK method is quite like, I think you understand, it's just exhaustive in terms of calculation. Rest of the concept is the same as the Euler's method. Okay, so okay, so let's look at this. What would we be finding here? We would be finding the trajectory equation. Okay, how does the height depend on time? That's what we would be finding. Now there is a certain approximation that we do here. We do approximate that gravity is approximately a constant. Now, when does gravity change? Gravity changes when you go to higher and higher levels. Okay, around the ground level, the gravity is assumed to be quite constant. Okay, so the force due to gravity is approximately a constant near the surface of the Earth. Okay, that's one of the assumptions that we make here. Now, why the negative sign? I told you this again. I'm taking this as a convention. Okay, so the height in the upward direction is positive. Okay, the force due to gravity is in the downward direction and hence negative. That is the convention I'm taking here. In other courses, do not use this convention. The basic idea is that you choose a convention and you stick to it. So you do mention when you're doing the problem or doing anything, you do mention the convention that you're using and then you follow it. Because different textbooks have different conventions. Some textbooks would not use the negative sign. Some textbooks would use the negative sign. So keep that in mind. Okay. So this is a revision question. Okay. This is these are essential concepts that you need to have known before. So I'm going to start the poll now. Let's look at the question once. What is the equation A equal to minus G? Okay, is it a partial differential equation with respect to your base variables y and t? Is it a first order differential equation with respect to base variables y and t? Is it an algebraic equation? It is a second order differential equation with respect to base variables y and t. So I will start the poll now. Okay. For poll 8. Okay, and you let me know what the answers are, because this is something that we discussed last time. You've got 50 more seconds. Wow. Somebody answered it's an algebraic equation. What on earth, Riyad? Like, seriously. No, the fact is that you're still saying that it is an algebraic equation when I kind of like made this comment. No, like I seriously don't understand. You're just doing it for, I guess, fun, maybe. I don't. 10 more seconds. Okay, so I'm ending the polling now and I will show you the results. Okay, so a majority of you did say that it is a second order differential equation with respect to base variables y and t. Yes, it is correct. Okay. I will just try to explain this to you. So what have I written? I've written A is equal to minus G. I've told you we are saying that G is a constant. So what is A? A is basically dV by dt, right? Rate of change of velocity with respect to time. If I write it in terms of y, okay, it's going to be d squared y by dt squared is equal to minus G. So what is it? It is a second order differential equation. So this is the correct answer that you have. Okay, I will stop sharing the results. But the funny part is that you guys still went on to answer it is an algebraic equation, even though I made that remark. Okay, so towards the end, I saw another person put in algebraic equation. Okay, I hope that doesn't confuse you because I boxed that particular thing. The answer is it is a second order differential equation with respect to base variables y and t. Okay, so let's move on to the next one. Okay, now we just discussed this. Okay, so if you still did not answer this, I'm going to be very disappointed. Okay, so if a rock or a feather were dropped in a hollow vacuum tube, which would reach the bottom of the tube first? Okay, if a rock and a feather were dropped in a hollow vacuum tube, which would reach the bottom of the tube first? Is it a rock? Is it a feather? Is it rock and feather at the same time? The rock and feather would remain suspended in the tube. The rock and feather would remain suspended in the middle of the tube. Tube is cut off. It is the tube. Okay, so I will start the poll now for that. Okay, these are important things that you should know. You should have known probably in your basic physics courses. Okay, you have about 45 seconds left. 30 seconds left. Twenty seconds left. Okay, I'm ending the polling now. Okay, and I'm sharing the results. Some of you still answered wrong. Okay, we just discussed this. We're talking about a freely falling body, right? Hollow vacuum tube. So it's freely falling body. What does hollow vacuum tube mean? There's no air resistance is what it means, right? So some of you answered rock, feather. Rock and feather at the same time is the majority, and I'm happy for that. But yeah, this is something that you should have learned in your elementary basic physics courses, right? At high school. You should have learned this at high school. What do you indicate? What does hollow vacuum tube indicate? Okay, it tells you. I will just stop sharing the results, okay, so that I can discuss this question. What does hollow vacuum tube basically tell you? It tells you that there is no air resistance. Okay, if there is no air resistance, we're talking about a freely falling body without any air resistance. Okay, and in such a situation, even if you have, say, a feather or a rock, okay, my feather is horrible, or a rock, it shouldn't matter. Okay, both should reach there at the same time. Okay, it would reach the ground at the same time. Some of you said it would remain suspended in the tube. What did you think, that the vacuum tube is something which is like anti-gravity or something like that? Okay, so with this, we have kind of like covered our essentials to deal with freely falling body. Okay, so let's just discuss this over again if you haven't understood the concept that we discussed last clearly. Okay, so if A is the acceleration of the mass of the object, from Newton's second law, we have F is equal to m into A. We equate both F and F gravity. Okay, so I've told you why the negative sign. The convention that I'm using here is this. Okay, and now it does not matter if the object is basically a stone or a piece of paper. Okay, it does not matter if it's a rock or a feather or a stone or a piece of paper. It does not matter if it's a fat person or a thin person. All of them will reach at the same time, irrespective if you do not have air resistance. Okay, so let's look at this. This is a problem that you're going to be getting. Okay, so it'll be asked a little differently. You wouldn't get the values. Okay, so you need to remember the parameters that you need to use. Solve the one-dimensional equation of motion for a falling object. Again, remember, one-dimensional. Okay, only in the y direction is what I'm doing. Y direction, because I'm talking about the height. I'm just talking about the y direction that's there. Okay, I really want you to be careful about this. It is not projectile motion, it's one-dimensional motion. Okay, so the input values could be y naught equal to y. Okay, some initial value that you get. These are initial value problems that you're looking at. So I'm sure you would have solved some initial value problems in your BSc. Okay, so you would get a differential equation, and they would ask you to get the particular solution to this differential equation based on the initial values that are given to you. Okay, so you would have y is equal to y naught, v is equal to v, okay, particular v naught, at a particular time t equal to 0 at the starting time. Okay, so that's the initial values that you have. You compare the results of this with different values of t and the exact solution. Okay, so you would have to calculate the exact solution for this. For such a differential equation, it's going to be easy, but when you incorporate air resistance into it, you see that solving the differential equation becomes a little more harder. What you need to do is you need to plot your y of t, and we haven't plotted v of t, but you can do that as homework. Okay, because we're going at a very slow rate right now. So here, what do? You use your y naught as 10 meters. Okay, that's given to you in the question. And here you have v naught is equal to 0. Now in your final exams, what's going to happen is they're just going to tell you solve numerically this freely falling body. Okay, so they're not going to give you the initial values. So you assume certain initial values and you draw a diagram and tell which way it is. Okay, which of the 6 ways it is going to be like, and then you explain that and you calculate this using Euler's method or RK method or whatever. Okay, so let's look at this. Okay, so we discussed this is a second order differential equation. You had an A here, but you're going to put that as minus G. Now, this is basically you're getting the exact solution of the problem. Okay, so first, what do? Okay, what was the differential equation we talked about? We talked about A is equal to minus G, right? So you can write this as a second order differential equation, d squared y by dt squared, which is minus G. You integrate the second order differential equation, and then you substitute the initial conditions. So if y naught is equal to 10, your v naught should be dy by dt, right? And that is going to be 0. If your y is a constant, it's going to be 0 at your t equal to 0. What are you doing? Basically, you're dropping the ball from a particular height, right? You're not putting any force on it. You're just dropping this ball. So the initial velocity of that is going to be 0. Okay, the starting velocity is going to be 0 at your particular time t is equal to 0. So once you put in these initial values to this differential equation and try to evaluate the constant, you get C1 is 0. Okay, this is basic algebra. And then what you would have here is you would have okay, so let me just clear the screen. Yeah, you would have this kind of a form because your C1 is 0. Right, and now okay, so this came up by mistake. Okay, so this is not supposed to be coming here. Now let's just integrate the previous equation that we found. What was that? What we got was dy by dt is equal to minus gt because your C1 is 0. Right, so when you integrate that particular equation, not this, but that first order differential equation we talked about. Okay, I should probably scratch this out so that it's more evident. You have y is equal to minus gt squared divided by 2 plus c2. Now you need to find out what the value of c2 is. So you plug in the initial conditions again. Okay, these are very, very easy steps. So I'm going to be going in on a very quick pace. What you have here is your initial condition. You substitute that and you get c2 as 10. Okay, so you substitute that, and this is going to be the exact solution of the freely falling body that you have. Okay, this is the exact solution. Y is equal to 10 minus gt squared. Okay, so let's look at this. Okay, so this is the plot of the exact solution. Okay, the points are not Euler's, the points that you got from Euler's method. The points are not the points that you got for Euler's method. I'm repeating that again. These are the points that you see when you have your when you have your exact solution. Okay, so here what you do see is that when does it hit the ground? Okay, so don't get confused. This is what I said. When you look at this graph, okay, this is basically y as a function of t, and this is t. Okay, so don't get confused with the way this looks. Okay, like a parabola kind of a thing. Don't get confused with this and the projectile motion. Okay, that's what I'm saying. In projectile motion, it's going to be the x and y that are changing. Here it's y of t and t. Okay, I hope you get that properly. Okay, so what you do see is that when does it reach the ground? It reaches the ground at 1.429 seconds. Okay, it reaches the ground at 1.429 seconds. So let's just keep that in mind. Okay, now, yeah, so these are the plots. Okay, so this is not from Euler's. These are the exact values that you have. Okay, by substituting it in the exact solution that you have, you get this kind of values. Okay, so let me just go on to this. Okay, so I want to formulate this again. This is something that we saw in the last class. Okay, we saw that this the way to formulate the Euler's method in the framework of your freely falling body problem. Okay, so what did we see? We saw that in the one-dimensional case, we can define your instantaneous velocity and acceleration like this. Okay, so this is very simple, and the motion of the particle is defined by this. Okay, so what is f of t divided by m? It's basically your acceleration, right? And what do you do in your freely falling body problem? You equate that to the value of gravity. Okay, so this is what we saw last class. Okay, so the last two slides, which I left as a cliffhanger, okay, for the next lecture, what we did see is that we could solve these two differential equations. Okay, what did we do? We took a second order differential equation which governs the freely falling body problem, split it into two first order differential equations, and we took these two equations and wrote it up in a form that is that's going to help you solve it numerically using the Euler's method. So how do we look at this? So when you looked at your Euler's method, you say, let's say you have a dy by dx is equal to f of x comma y is what you had. And when you looked at the Euler's method, you had yn plus 1 is equal to yn plus f of x comma y into delta x. Okay, this is what you got from your Euler's method, right? Now, what you just have to do is replace this y by a v. Okay, so you have vn plus 1 is equal to vn plus the acceleration due to gravity, which is here. Okay, so that is basically your f of xy. I hope you see the relation. Okay, even though I haven't written down Euler's method formula here. So this is basically your function f of x comma y, this part, and then you multiply it with delta t. Okay, now this only solves the first part, the first ODE. Now you have another ODE as well. Okay, that is the one to do with the trajectory. So here you have y of n plus 1 is equal to yn plus v of n into delta t. Both of them, you're incrementing it in terms of your time. Okay, for both of them, for velocity as well as your height, you're incrementing it in terms of time. Okay, so now let's look at this. Okay, so let me just review that. What is your aim? Your aim is to find y as a function of t. First, what do? You find v as a function of t, and then you find y as a function of v. Once you find v, you can find out y from this. Okay, so first, what you do is you use Euler's method and find out v, take that value of v and plug it into the next equation. Okay, so it's basically like doing Euler's method twice. Okay, so if you understand what I mean by that. Okay, so these are the equation for a freely falling body for Euler's method. So you have vn plus 1 is equal to vn plus minus g into delta t, and vn plus 1 is equal to, yn plus 1 is equal to yn plus vn delta t. Okay, why is that? Because we're taking, see, the idea is that your f of x comma y in this equation is acceleration, which is minus g. And here in this equation, your f of x comma y equivalent, okay, it's not that it's dependent on two variables. The equivalent is basically like your velocity. And that basically you understand when you have dy by dt equal to your v. The reason I'm keeping on repeating the points is because somewhere down the line, if you do kind of like mess up or your attention goes haywire, you can kind of like catch up back. Okay, so I know I'm doing a lot of repetition in that. Now here, let's look at this. Okay, let's look at the solution based on your Euler's interval for delta t equal to 0.5. So your vn plus 1 is equal to vn minus g of delta t. Okay, this is pretty simple to calculate. What is your interval? Your interval is 0.5. Okay, so your 0.5 interval, you will multiply it with 9.8, and then you have v of n, which is your, if you're doing it for the first iteration, you will take your initial velocity. And then you will take initial velocity itself here. Okay, so you do not take the vn plus 1, but you take vn. Let me just point that out. Here, do not take vn plus 1. Do not take vn plus 1, because that is the basic mistake that you're going to make. You take vn itself. Okay, that's the way it works. And what you do see here, you do see that values are repeated twice. And why is that? Because the initial velocity that you took in here is 0. Therefore, this term is gone. Okay, so yn plus 1. So if you're y1, it's going to be equal to y0. So you do see that there is a repetition of the values here. Okay, but that is the way to go about it. Don't think that you made a mistake. It is the way to go about it. Okay, so I think this is probably, you guys should have this in your head by now because you've done the homework. You've done your RK method homework. So you should probably have this Euler's thing in your head by now, because it's pretty simple comparison to your RK method. Now, let's look at this. This is basically a delta t when I've increased the interval. In the question, they have kind of like said, do it for 2 intervals, right? They've said, do it for different values of delta t. So what do you see when you do increase the value? Okay, fine. Yes, the first one remains as such. Because why? Your initial velocity is 0. You're just dropping the ball. When would it change? It would change when you put a thrust on the ball and you throw it upward. So if it is going to be like this, okay, so let's say you throw the ball upward and it comes down, and you have certain initial velocity, say v0 equal to 20 meters per second. Okay, if you have certain velocity like that, then this whole thing would change. Okay, otherwise, if it's a free fall, the first value that you get for your trajectory is going to be the same as the initial value. Okay, so y1 is going to be the same as y0. Okay, so now we've discussed that. Let's just look at this. Okay, so what happens when you decrease the size of the interval? Okay, so the green line that I have here is for a bigger size of the interval, which is 0.5 seconds. The blue line that I have here is going to be for a smaller size of the interval, which is about 0.25 seconds. This red line basically is the actual value. So you realize again that as you decrease the interval size, it comes closer and closer to the actual value that you have here. Okay. So now I want to just share this with you. Okay. Not that it is relevant here right now, but the thing is that how can you do it for any problem? Okay. Here I've just specified that the velocity is 0 and the initial velocity is 0 and the value of y0 is 10 meters. I've given you the values. Let's say those are arbitrary. Let's say v0 is still v0 and let's say y0 is still y0. How would the exact solution look like? Okay, so we know that the differential equation governing free fall is a is equal to minus g, and this is how you get it. So you integrate this to get the first solution. So you integrate this, you get b is equal to integral minus g dt. This is not the Euler's method. Let's be very clear on that. This is the exact solution that I'm doing. I'm solving the differential equation and showing you the answer. Okay, you have a minus gt and you add it with a constant. Okay, so for this particular initial value problem, what do you have? I'm going to say it's an arbitrary constant v0. Okay, I'm not going to be saying it's 0 meters per second. I'm saying it's an arbitrary constant v0. So you substitute that and you will end up getting, okay, so this should be, this is not, no, this is not frequency, it's velocity. Okay, some kind of a typo. Now here, what do you have? The first order differential equation. You end up getting a first order differential equation again. So you need to solve that first order differential equation. Okay, and this is pretty simple. You all know this beforehand. Okay, it does not look, it seems complicated, but it is not. Okay, so what do? You integrate this and then you find out this value. Okay, over here, so you get this kind of a form. Now what is c0? C0 is basically the initial height. Okay, so if you put any constant of integration along with, say, this parameter. Okay, so if this is in meters, let's do some dimensional analysis. If this parameter here is in meters, the constant should also be in meters. So you kind of have this intuitive feeling that the constant of integration should be a let's say, should be a height. Okay, so let's say it's just the initial height. Okay, now in the other case, what did you have? You had v. Okay, so this constant of integration, if it was there, okay, if it was there, it should be having initial velocity, right? So here you will have a v0 associated with it. So the constant of integration would be a v0. Okay, when you do your dimensional analysis. So that's kind of like a trick to remember what your constant of integrations units might be. Okay, so now let's look at the air resistance problem. Okay, so this is a complicated problem because we have two different types of, well, the resistance has basically two different ways which we can represent. One of them, yes, you can solve, and the other one is a pretty tough equation to solve. Okay, so you have to use a lot of other different functions coming into the picture, but we won't be doing that. The idea of using numerical method is to solve differential equations that you cannot solve by hand, that you cannot solve in your head, right, immediately. So we would be using the Euler's method to solve the differential equation numerically. Okay, so that's the whole idea. So now let's look at this. What is the effect of air resistance? So the drag force, okay, we always think of the drag force is in a direction opposite to the velocity. So if the ball is going in upward direction, the drag force is going to be downward. Okay, and if the ball is going in a downward direction, okay, if the ball is going in a downward direction, the drag force is going to be upward. Okay, so this is free falling. Okay, we'll be only looking at this particular system. Okay, this particular free body diagram, and this is basically your moving upward problem. Okay, so we will just be focusing on this for ease of solving the whole thing. Okay, so let's look at this. Okay, so the assumption is that drag velocity is force is velocity dependent. Okay, so drag force is velocity dependent, and one of the things that I told you is to note the drag force is opposite to the direction of the velocity of the object. And how do we have this velocity dependent? So when we're looking at velocity dependent forces, you have your drag force F proportional to the velocity. You also have a drag force which is proportional to the velocity squared. Okay, so the differential equation that you get from this part, okay, the ODE that you get from here is going to be a little bit more complicated, but this is something that you can solve. Okay, and probably it would be as a homework for you to solve it, solve the exact solution, not using Euler's method, but to get the exact solution that I will probably let you know in the future. Okay, so let's look at the type 1 velocity dependence. Okay, so the form of the velocity dependent force of the resistance of air is given by Fd equal to kV. Okay, is proportional to velocity. Now, what is K? K is basically a parameter that depends on the properties of the medium and the shape of the object. Okay, so K will differ for, let's say, a rock, and K will differ for a feather. And that's how you have a feather probably standing much, just floating up in the air, whereas a rock hitting the ground. So this is what constitutes the difference. Now, let me tell you that this is not the exact value. Experimentally, we have kind of like found it's kind of like closer to this kind of a dependence. But of course, there are other factors that are going to be coming into play. There's going to be wind, there's going to be other rotation of the earth, acceleration due to gravity, the height at which you suspend the whole part, the height at which you drop the ball. Okay, so there's going to be a lot of other dependence as well. It's not just that, it's just velocity dependent. It's not just dependent on the velocity of the body, properties of the medium and the shape of the object. It can have other dependence as well. Okay, so let's look at this. Okay, so now you would have your terminal velocity coming in. So when the drag force is equal to the weight of the body, okay, the weight at which it is coming down, or the force due to gravity, then you have this kind of like suspended over there. Okay, right? So what you have then, you have this terminal velocity that you approach. Okay, it would still be falling down, but what you do see is that there is no acceleration. Okay, it would still be falling down, but there would be no acceleration. That's what you kind of like inferred from here. Okay, so if G increases as V increases, there is a limiting terminal velocity. Okay, so that is a limit, that is a maximum velocity at which you can hit the ground. Okay, so your F of D is equal to F of G, and you have your mg, and this acceleration kind of like vanishes. So you have V of T is going to be mg divided by K. Now let's look at this in terms of your terminal speed. What is your force? Okay, so let's just go back and look at this. What have they asked for? They've asked for Fd, right? So in terms of your terminal speed, the drag force can be written in this manner: mg into v divided by v of t. What you've done is basically you've replaced the k in terms of your terminal velocity. So once you do that, what you do find is, okay, so this is going to be drag force in the upward direction. So it's going to be positive. What is falling down is negative. Okay, so you have a minus g, mg, and you also have a plus. Okay, so that's going to be, you're adding up the forces. Okay, so don't get confused with that. Okay, this is why you get confused with the direction of the forces. Keep that coordinate system in mind, and that's how you go about it. So you have mg into v divided by vt. You take your minus mg out, and this is what you should be getting. Now let me just be very clear on this. Certain textbooks do indicate a negative sign. Okay, here sometimes you take it along with a constant. Okay, so let's not put a negative sign because it's really confusing. It gets really confusing. We will take it along with the constant. Okay. Okay, so let's look at the type 2 dependence. Okay, so this can be a question. Okay, they'll give you the dependence of your drag force, and they will say derive the net force on a falling body using this expression in the units of terminal velocity Vt. So what you need to do is you need to take this K2, convert it in terms of terminal velocity, and then add up the forces so that you get the net force falling on an object. Okay, so this is the form of your velocity dependent force. Okay, K2 again depends on the properties of the medium and the shape of the object. And what you have here is you calculate the terminal velocity. So now you realize there is a different kind of dependence, not a linear dependence, but a different kind of dependence. You have a quadratic dependence that comes into the picture. Okay, so as F increases, your V increasing, and there is this limited terminal velocity that you reach. Okay, After that, you do not go beyond that terminal velocity. Now, in terms of the terminal speed, what do you have? Your FD is equal to mg v squared divided by vt squared. What do you do? Basically, you square it and you substitute it. You get the value of k, okay? You square it and you substitute it back, okay? So that's what you're basically doing here. And then you add up the forces and this is what you get. So you have minus mg into 1 minus v squared divided by vt squared. Okay, so now that is done. This is your problem. Compute the speed at which the pebble of mass m equal to 10 to the power of minus 2 kg reaches the ground if it is dropped from rest at y naught equal to 50 meters. Okay. Now, okay, I'll come to that point later on. Wait. Okay, so let's do this. Okay, so compare the speed of that of a freely falling object under the same conditions. What are they saying? You use your Euler's method itself. Do it for a velocity dependent. Do it for free fall and compare both of them, okay? And assume that the drag force is proportional to v square and your terminal velocity vt is 30 meters per second. So this is a problem that is given to you, okay? You've got the mass, you've got the terminal velocity, you've got your initial height, and you've got the way your drag force is dependent on the velocity, okay? So you put the ODE into such a form. So you put it in the form of dy by dx is equal to f of x. Okay, and then the solution to that, this is basically Euler's equation revision, yn plus 1 is equal to yn plus f of xn, yn delta x. Now you have this governing ODE in the problem. So you have f is equal to m dv by dt. What is the governing ODE? You have air resistance. You also have a dependence of v square. So we just did that equation. We just found out what the value of f was. So you have minus mg into 1 minus v squared divided by vt squared. Now, what is this? Basically, this is your f is equal to m into a, okay? Right? And then you write your dv by dt in this form. Now, once you get your first order differential equation in terms of your v and t, okay, you start to use the Euler's method and start to compute your v value. So vn plus 1 is equal to vn plus minus g into 1 minus v squared divided by vt squared into delta t. Now, have you noticed that there is no mass here? So just because that there is no mass here, does it mean that it is not dependent on the mass? Where does the mass dependence come from? Okay, where does the mass dependence actually lie? The mass dependence lies in your terminal velocity. So since they've given you the terminal velocity already, the mass is considered to be like kind of like taken along with that. Okay, the way we've kind of like framed the equation. If you do not get your terminal velocity, you would have to get the parameter k. You would also have to get the mass. Okay, so this data that they've given here in this question, they've given the mass here. It's kind of like redundant because they've already given you the terminal velocity, which contains what? K2 is what I've written, K2, and it also contains mass. Okay, so that data is kind of like incorporated into this. So this data is kind of like redundant. So don't get confused with this. Okay, the way I've written the equation here seems like there is no mass dependence. Okay, but there is a mass dependence. Where is the mass dependence? It's there in this guy, the terminal velocity. So let's be very careful on that. Okay, so here what do you have? Given v of t is 30 meters per second. That's what is given. Okay, so the terminal velocity is 30 meters per second. You substitute that, and then you just have to do your Euler's equation. So what is this guy? Okay, let's just compare it again. What is this guy? This guy is basically your f of x comma y in your Euler's equation. Okay, because you've written it in this differential equation form. Let's say this. Okay, so if it's dy by dx, you have f of x comma y. Okay, so now you get the whole idea. Okay, I am not going to be doing each and every point here. What I will tell you is that this is the number of points that I have computed. Okay, so I've done about 15 points, not necessary. You can stop with 10. More than 10 is just too much. Okay, so what is the initial height we started off with? We started off with 50. Okay, we started off with an initial height of 50. And what do you see? It's decreasing. The V naught here is negative, just as in the other case where we assume that it's negative. Why is that? Because the ball is dropping down. Okay, so downward direction associated with the negative sign. Okay, the height, what is happening? Basically, it's decreasing. Okay, so it's going up to 0. It's going to fall to the ground. Okay, now you do see that there is a negative -4 that is here. Basically, what the computer it cannot stop exactly at the ground level. Okay, it will stop in terms of the interval. Of course, if you shorten the interval to say 0.1, 0.05, it's going to stop exactly closer to the ground level, not exactly. It's always tending to. When you're using numerical methods, you always tend to the answer. You never really get to the answer. Unless, of course, the equation is pretty simple and straightforward. Okay. So what do you have here? If the drag force is proportional to v square, okay, this is along with your air resistance. How does it look like? Your height kind of like decreases. The velocity kind of like will reach a particular terminal velocity. Okay. And then what we can do is we can compare it with free fall. Okay. So this is no air resistance at all. Okay. We do not have a drag force here. This is free fall where you have, let's just go back, where you have your differential equation d squared y by dx squared equal to minus g. Okay, so you do not have that parameter minus g into 1 minus v by vt squared. Okay, you do not have this particular term there. Okay, now let's look at this. So let's compare. Okay, the reason why I want to compare is we can infer a lot of stuff from here. Okay, so when you initially start off 50, 50 is what you get. The third term is also same, 49, 49.3875. But when you reach here, okay, so this is without air resistance, you do see that it is at a height lower as compared to that with air resistance. Okay, so let's say this is 48.16659. Okay, this is with air resistance. Okay, what happens? You're kind of like you're kind of like reducing the effect of gravity when you have air resistance, right? So you kind of like it's going to be going upward, right? The resistance is upward, force due to gravity is downward. So this is what you have. And then if you compare this, you have 48.1625. Okay, so now initially you do see that the value is kind of like the same for with and without air resistance. And why is that? Why does that happen? Okay, so let's just look at why that happens. Let me just get the spotlight out. Yeah, okay. So this is what you do see. Okay, so I plotted these 2 points. The orange line is basically your free fall. Okay, so that means it reaches the ground faster when during a free fall, whereas the purple line is basically with your air resistance. Okay, and initially, do you see here that it's kind of like coinciding? And why is that? Because initially the velocity, the initial velocity for both cases is 0. So when does the drag force kind of like, what is the drag force dependent on? The drag force is velocity dependent is what we're assuming. So if there is no velocity initially, you're going to get the same values there, right? You're going to get the same values as without air resistance. I hope you get that point pretty clear. The idea is that the drag force that you have is basically dependent on velocity. Initially, for both cases, with and without air resistance, what do you see? You see your V0 is 0, right? Your V0 is going to be 0. And when is the drag force coming more and more into the picture? The drag force will come more and more into the picture as your velocity increases. So when is your velocity going to increase? When you drop it and then you kind of like reach the bottom, that is when you have your most velocity. Okay, so you'll have a maximum velocity here that's going to be happening. Okay, so initial velocity is 0. The maximum velocity that you have is around when you reach the bottom. Okay, unless of course you reach the terminal velocity before that point. Okay, so this is kind of like pointed out. Now what do we have? Okay, so initially the values match with that of the free fall. That's what you saw in your plot. Now, because the drag force is small initially, as your initial velocity is 0, and only increases gradually as you go further into the motion. Okay, so in time we see that the drag force gets larger and larger as your velocity builds up, and therefore it remains in air for a longer time. Okay, so now let's do this. Okay, so let's do a poll. Okay, to kind of like wrap it up. Okay, so let me do drag force. So I will launch the poll. Let's just read the question. The parameter k in the drag force equation depends on the shape of the trajectory, terminal velocity, shape of the object, and initial velocity. Okay, so I'm launching the poll now. Okay. 45 seconds left. Thirty seconds left. Fifteen seconds left. 'Okay, I'm ending the polling now. Apparently, all of you guys answered terminal velocity. Okay, so I knew this would be a bit of an issue. Okay, I knew this idea would be a bit of an issue because I told you a way to find out the terminal velocity would be to use this parameter k. But what are you doing here? Okay, so let me just share the results and show you what you guys have answered. Okay, kind of like majority of you answered terminal velocity, which is wrong. Okay, what is it? It is basically the shape of the object. Okay, why is that? Okay, we did discuss this before, right? We did mention, let me just go back to that slide. Okay, when we did discuss the velocity dependence, what did we see here? Okay, so we said that the drag force Ft is equal to K2 V squared, and your K2 or K for that matter depends on the properties of the medium and the shape of the object. Okay, here what are you doing? You're basically calculating terminal velocity based on this. Okay, so does it mean that, let's say you have the same terminal velocity? Okay, does it mean that the object is the same? No, it does not mean that. Okay, so your G can vary based on whatever planet you're shifting to, right? So it does not mean that just because you have the same terminal velocity, the object that you have is the same. The object identifies itself with the parameter K or K2 for that matter. So what are you saying? You're saying that basically, just because you saw a dependence, you saw a relation, does not mean it's going to be dependent on that. K is irrespective of the terminal velocity of the object. Okay. So let me just go back to that poll. Okay, so the drag force here, what you do have here is the parameter K in the drag force equation. It depends on the shape of the object or the material of the medium. Okay, next thing that you do have is, this is your homework. Okay, you will have to compute this. I told you that there were two types of velocity dependence. You have proportional to V and you have proportional to V square. Okay, so what we did was we did the hard one. We did V square. This one is what is going to be given to you, and I will send it to you by email. Okay, I will send the form by email. Now, yeah. Okay, so this was a previous year question that you got. Solve the governing differential equation for the trajectory of a freely falling body. You do not write whatever I've explained to you here. Okay, you do not write the entire thing. You cut short the whole thing. Okay, so solve the governing differential equation for the trajectory of a freely falling body. You will solve it explicitly, and you will solve it numerically by using small delta t. Okay, small delta t, so that you can reduce the number of iterations that you have. So you do both the explicit as well as because this is a 10-mark question. Okay, so you have to write a lot more. So based on the marks of the question, you adjust it. What do? You do the explicit solution and you compare it with the numerical solution and say, oh, this is what you've got. Okay, so you've kind of like done both. You've been being safe. Okay, if you run short of time, just do a numerical solution and go ahead. But they would expect you to solve this along with air resistance as well. That's what I'm thinking, because I remember doing this along with air resistance when I wrote the question last time. Okay, so yeah, so this is it.